So the rotation is along the fixed axis of rotation, and this fixed axis of rotation is said to be this point. Okay, this is the center to which we will have a rotation. So what is the torque? It is the rotating force. Its action is same as that of the force itself, but it is a rotating force. Sum of product of masses of every particle with square of the distance from the axis of the rotation. Hello everyone, I'm Brinda from Department of Physics. Let us just start with session 1 of chapter 7, and that is your system of particles and rotational motion. So in today's class, we are dealing with system of particles and rotational motion. So whenever this concept comes to your mind, system of particles, what kind of a particles here we study? Here we study the rigid bodies. So what is meant by a rigid body? The object or a body which is having a perfect and a definite, that is the one which is having unchanging shape, the perfect, a rigid shape or a definite shape. Such kind of a body is called as a rigid body. The rigid body here, it undergoes two types of motion. One is translational motion, one is rotational motion. In order to know what is translational and what is rotational, here we go. Translational motion means motion of a particle which is along with the motion of the objects. The objects is having, suppose this is a cube, this has got a particles P1, this is suppose it is P1, this is P2, P3 respectively. Whenever it moves from one place to another place, all the particles also move along with the object. So such kind of a motion is called as a translational motion, as you can see here. Along with the object, even the particles of that object also moves. So next we are going on to rotational motion. So here it's a motion of the particles are in the same interval of time. Okay, so we can consider a rolling motion. So point is fixed, but it is rotating in a axis, same axis, but its particles will not have the same motion at same interval of time. Okay, so the rotation is along the fixed axis of rotation, and this fixed axis of rotation is said to be this point. Okay, this is the center to which we will have a rotation. So as you can see in this diagram, this is a fixed axis of rotation and it's getting rotated. So that is how exactly we study about this rotational motion. So we are clear with translational motion, rotational motion of a rigid body. Rigid body means the one which doesn't change its shape. Next we have center of mass. What is exactly the center of mass? It is a point at which the whole of the mass of the body, that is also called as all the masses of the system of particles, appears to be concentrated at the center. How many, if suppose n number of particles are there, all the n number of particles mass is concentrated in the center. That is the grip where it holds. So in order to calculate this, we have got a diagram such as, suppose if there is a mass m2 here and there is a mass m1 here in case of this x-axis, then the center of m2 as well as m1 turns out to be this point. So on extension of this point, we can just name it as m1 is in the distance from the origin, that is x1. m2 distance from the origin is said to be called as x2. So the distance from origin to the center of mass, we call it as m, is known as capital letter X. Okay, so when this is a condition, we know that the center of mass of the system can be equated as m1x plus m2x, that is with respect to the center of mass, is equal to m1 x1 plus m2 x2. That is the mass with its own distance, mass of the object with its own distance from the origin. So what happens to this? We retain only m1 plus m2, take common outside as x is equal to m1 x1 plus m2 x2. So x remains there. X is nothing but the center distance of the center of mass from the origin. So what we get? m1 x1 plus m2 x2 divided by m1 plus m2. This holds good for the system of particles. The center of mass of the system of particles is calculated in this manner. Suppose if there are n number of particles, this is for two system of particles. Suppose if there is n number of particles, and then it turns out to be x is equal to m1 x1, m2 x2 plus it goes up till mn xn. Similarly, we will have a denominator as m1 plus m2 plus it goes up till mn. This is how the condition looks like. Okay. So instead of writing the complete thing, we can sum it up as x is equal to summation of I is equal to 1 to n mi xi divided by mi. So we know that summation of mi can be called as summation of mi xi divided by, it is capital letter M, that is center of mass, what it gives, and x is nothing but your distance of the center of mass. This is how exactly the summation look like for a center of mass. That's all about your center of mass. So what is again a center of mass? The point at which, this is the point at which whole of the mass of the body or all the masses of the system of particles appear to be concentrated at the point, at certain point. Okay. So next, this is what we have done in the previous concept, that is considering line joining two particles in case of x-axis. So this is what I have told, m1, x1 is the distance, m2, x2 is the distance. So this is center of mass of the point where exactly m lies. So x is the distance from origin towards that point. And next we have torque and angular momentum. So we shall see what is a torque and what is a angular momentum. Torque is the one which causes rotational motion. So it is a torque means it is a rotating force. So what is a torque? It is the rotating force. Its action is same as that of the force itself, but it is a rotating force. Okay. It causes rotational motion of an object about one or more axis that passes through the center of mass is what you will have to remember. And it is also called as moment of force. That means rotating force. Okay, so of a rigid body in the combination, what sort of a combination it has got? It has got two types of motion combining together, that is rotational motion as well as translational motion. So now next is torque, means moment of force. As I told you, that is also called as rotating force. Two types, one is moment of force also you can even call as a rotating force. So how is it defined? It is defined as the force which tends to cause a rotation of object along the axis. So suppose if this is the axis and there is a rotating force, rotation happening there. So it's a force which tends to cause the rotation along this axis which is extended, which passes through the center of the mass. So for a circle, suppose if there are n number of particles surrounding it, the center of mass turns out to be the center. So through which the axis passes. So that is called as your torque. Next, let us see the relation between torque and angular momentum. So now, first of all, what is this torque? We have studied in the previous slide, that is torque is a rotating force and it is represented in terms of tau. Okay, so it is nothing but torque is the product of R as well as your F. So it is the product of your position vector as well as the force. Okay, this is the time rate of total angular momentum of a system of a particle about a point is equal to sum of external torque acting on the system taken about the same point. So this is the exact equation statement for the relation between torque as well as angular momentum. And we have after having a torque equation, we have an angular momentum equation given by vector L, which means to say it is the angular momentum which is equal to the product of position vector with respect to momentum vector P. Okay, so we have two concepts over here. With respect to this, let us just check out the position vector as well as your momentum. Having this concept, that is just take the angular momentum is equal to vector R into vector P. On differentiating this by using a product rule, we have dl vector divided by dt is equal to retain your R dp by dt plus P vector is equal to dr by dt. We have m and v vector. So m into p is equal to m into v. Mass is constant, so we can take mass outside. Velocity with respect to time is nothing but your acceleration. So it turns out to be, this concept turns out to be f. So I can just write r into vector f. And here we have momentum P, so we can just write it as m into V, and dr is nothing but displacement with respect to time. Here also we can just write it V. Product of two V's gives you 0, so it turns out to be 0 itself. That is V dot V concept you have studied. So now we are left with dl by dt and r into F, nothing but this product of position vector with respect to force. So we just get this final answer as dl vector divided by dt is equal to tau. This is the relation between your angular momentum as well as your torque. So the time rate of change of total angular momentum of the system, that is this, of a particle at a point is equal to sum of the external torque acting on the system taken at the same point. This tau can be sum of many system of particles, have each particles as having a torque. You can sum it up with respect to the torque as well. Sum of the torques gives you this condition, okay. So that is all about your relation between torque and angular momentum, which is one of the important concept. Next we are going on to conservation of angular momentum. So we actually know that angular momentum is given in terms of dl by dt is equal to torque. That is the relation between angular momentum as well as torque. How did we get this? By projecting torque as the product of position vector with respect to the momentum, correct? Because of this, we have got this condition. So when can you say that the angular momentum is said to be conserved? That is, when the torque acting on the particles is said to be 0, then we can call dl divided by dt is said to be 0 when an angular momentum is said to be your constant. So it is said to be conserved. So conservation of angular momentum holds good with respect to this, that is when torque is 0. And next we are going with respect to moment of lever. So what exactly is this moment of lever? So here we can see it's a sum of product of masses of every particle with square of the distance from the axis of the rotation. So moment of inertia here, inertia is given in terms of I. So when we just inertia in terms of I is equal to sum of product of masses of, that is sum of product of masses, maybe m1 as well as m2 of every particle with square of the distance. So square of the distance of particle is this one. So r1, and here comes out to be r2 from the axis of rotation. Suppose if we are taking a rotation motion and this is the axis, this is for a particle P1, this is for a particle P2. If suppose this is P1 and P2, this is having mass m1, this is having mass m2, and this, since this is the axis of rotation from here to here, the position vector is r2, r1. Sum of masses m1 and m2 and their square of the distance between the two particles. So this holds good with respect to your moment of inertia. So this is the equation for it. This is also one of the most important concept. So in system of particles and rotational motion, few of the important topics have been done with respect to your syllabus. So now we have completed some topics of system of particles and rotational motion, which is there in your syllabus. Let us all meet in our next upcoming session with the next new chapter. Until then, have a good day. Thank you.